All right, let's get started. Hello, everybody. Hope you're all well. It's really nice day out, and in the nice in the sense that it's overcast, and it's actually a really good day to sleep in. I wish I could have slept in, but not going to do that. But yeah, let's actually jump into it. So to start off today, there are some announcements that I want to make you guys aware of. And one of these is hot off the presses. Like I literally got the email like 3 minutes ago from the math department. So one, I want to remind you that the last day to apply for the pass fail option, I believe, is today. That was mentioned in the email. I didn't verify through any other source, but the email mentioned that. So that's what I'm saying right now. Also, it seems that according to the deans, and the math department is going along with this as well, each instructor has their own freedom of what to do for finals. So that being said, I don't have to worry about anything. They gave you some guidelines, of course, but I don't really have to worry about us doing it another way that we're not used to. So pretty much what I will say is that I'm just going to continue what we're doing for the test. We'll use the same protocol for the final. I really have, I think it's going to work out. And I probably didn't mention this to you, but we are going to be using I've been mentioning, I don't remember who I said it to, but we're going to be using the platform Top Hat to do exams. And today, tomorrow, sometime over this weekend, you guys will be receiving an email on how to sign up for that. So the exam is going to be online, it's going to be proctored, it's going to be timed, all that good stuff. And that's the platform we're going to do it through. So no additional costs. They adhere to FERPA guidelines, so your privacy will be protected, all that good stuff, all the things that I wanted to make sure happened are happening. And I uploaded some practice tests to the platform already. I feel like it's a good way to go about it. So you would log into the platform, questions will be on the screen. You'll actually write this out on paper. You'll write out your solution. You'll get your answer. And you're not going to put the answer in the computer because I think it's annoying for you to have to type an answer into the computer. So you're just going to type something to acknowledge that you've done the question. It's going to mark it that, okay, this question was done. And yeah, you're going to go through that, do the other problem, done, do the other problem, done, move on to the next question, do the other problem, done, okay. You move on, and at the end, you're pretty much going to scan your work and send it to me. So there's also an app through the same platform where you can scan from your phone and upload it right to the platform. Or if you want to scan to your computer, if you have a scanner at home, PDF it, and then you can upload it from your desktop or laptop or whatever. But that's how it's going to work. So the online exam platform that's going to be used for the test, we're going to use the same thing for the final. And yeah, that's it. In that regard, that means our test is on Wednesday during regular class time. So if you are in, Lauren is coming in. So if you are in the 10:30 section, your exam starts at 10:30. If you're in the 11:30 section, your exam starts at 11:30. So I'll give an exam for each class individually. It will be online. It will be through the platform Top Hat. What I also want to do, I'm giving a lot of exams next week, so I'm hoping something like this can work out. What I also want to do is to do an extra practice test where you take it online. So if I can get through that this weekend, in an ideal world, I will get through it and we'll actually do a dry run. So I'll probably have you guys do like a practice for the online test on like Monday or something like that. And that won't, I'll try to see if I'm gonna actually talk to them again today. I'll see if I can leave the window open for you to just log in at any point, take the test and then log out. And yeah, just to get used to how it would feel. I don't want anything to be surprising. So yeah, what else do I want to say? Oh, yeah, so I think that's it. So last day for pass fail is today. Final protocol is following the same protocol for exam 2. You will receive an email giving you details on how to access the platform that will be used in exam 2 and the final. And in an ideal world, we'll actually get a practice on using this platform before exam 2. So, but we'll see, because I'm giving exams to all my classes pretty much every day next week. So I'm hoping I'll find the time to actually set up a practice final and have that run just to see how it will go. But yeah, I think that's how we're going to do it. Feel really good about it. It's been a while since I could be optimistic about anything, but I think this is going to work out. I think it's going to be fine. So yeah, that's what we are doing. Now let's actually get into the class here. Well, that's not us. That's Calc 2. We are 1203. We are 1203.
I have a question.
Yeah, hold on. Yes, this is where we're. Okay. All right. Go shoot.
Will the final still be on May 12th?
Yes. So as far as I know, the final exam schedule did not change. So whatever was in the syllabus as to what day your final is supposed to be. Hold on. Let me actually. That's it. Okay. So now. Is this your class? Because someone had asked me this earlier, so I looked up our syllabus. Okay, so this is 1203, that's you guys. And if you scroll down in the syllabus under the topics list, yeah, so we're stopping here. So these time permitting topics we're not gonna do, even though I am talking about some applications, errors between curves is included in that lecture. Integration by parts we're not gonna do. So if you're in section RO3, it's May 5th. So it depends on your section. My 2 sections are taking it different days. So RO3 is taking it May 5th at 9:30, and RO4 is taking it May 12th at 1:30. And the academic calendars are actually linked here. And last I checked, it didn't really change. Yeah, so this was what was there last time. And so you'll realize that if you're in Tuesday, Wednesday, Friday, at 10:30, which is one of you guys, your final is May 5th. And if you're at 11:30, your final is May 12th. Yes, so this is, I'm literally on Fordham's website right now. That is what is currently posted as of today. I don't think the schedule is going to change after today. So yeah, so the finals are still what was indicated in the syllabus. So I've been given no indication or information that the final exam schedule has changed. So whatever was there is going to be what it is. Now, what was not clear was the location and seating assignments, which now we know. You will be taking the final at home in whatever location you want. So yeah, so that's how that's going to go. So the final exam date will still be the dates indicated in the syllabus since the beginning of the semester. Okay? Yeah. Other questions?
I have a question about the test program.
Yes.
So is it like an app that you have to download on your computer, or can you just download it on your phone? Like, does it require a video camera?
Yes, it will require a camera.
So is it an application that you have to download onto your computer?
No, it will be something that you can go through a browser. So you should use Google Chrome, and it will have a Chrome extension attached to it.
Okay.
So it'll be through a browser. You won't need to download any programs or anything like that. There is an app that you can download on your phone. That is optional though. That's if you don't have a scanner. So you can get the app on your phone, and so you can actually scan to the by taking a picture on your phone and upload it through the app. So there's that component to it, but that's not 100% necessary. If you have some other way of scanning the document, you can upload it through the browser as well on the website. So you'll actually be going to the website. And emails about that will be sent out this weekend. Today, tomorrow, latest Sunday, I'll send out an email introducing you to the platform and inviting you to go and sign up for it. But it'll be through a browser. Any other questions?
Will you upload the answers to the practice quiz to the website?
Probably not. So what we'll do is today, I'll probably get through this with enough time for you to have some questions at the end, and you can ask me more questions on Tuesday or in office hours. So.
Okay.
But yeah, with moving everything online and me trying to get all the exams in here and getting a practice exam up, I probably won't have time to write out all the solutions to all the practice exams. I've been writing and uploading them at this point. So also in an ideal world, what I would say I would want to happen is I would create another practice test for you guys and have you guys actually take that on the platform. So maybe like Monday or something like that. And again, that is time permitting because like I said, I have a lot of exams, but I'm aiming for that. That's what I want to do. So I'll send out emails that will tell you guys how to sign up for this thing. And then I'll actually release a practice test on the platform, which you can log in at some point on Monday or Tuesday and do the exam, just to try to see how it feels, make sure you can actually submit questions properly and all that good stuff. And then on Wednesday will be the actual exam. And all going well, we will continue that for the final. Okay. All right. Let's actually just run into this. So integration, nothing really new to learn in terms of that, but we were looking at applications of integration, things that we could do with integration. And we saw word problems that we were able to solve that before integration, we couldn't have done this. We knew how to solve the motion problem in one direction using differentiation, but to actually go back, if we don't have this data up here, we have the data down here, we can actually go back in that direction using integration. So we saw an example of that last time. And yeah, so we did that exam. You guys were supposed to try the practice exam yesterday and have some questions today. So let's just get through this and we will then pause for some questions. I think we'll have time at the end of today to do some questions. Let me pull this thing in. All right, so now we're going to talk about areas between curves. And this is one of the main applications for us because that's how we introduced integrals as a way to find areas. So the idea is, we know the integral is something that finds the area under a curve, right? So this is, say, f of x. And if I want to find the area under f between a and b, this was given by the definite integral from a to b of f of x dx, where f of x is just going to be some formula, and we know how to compute this number for certain special formulas. However, now I want to actually figure out how would we do this for area between curves. So let's say I have two curves. That's a g of x, and this is an f of x. And I wanted to find the area in between them. Now, either I'm given an interval, so I can say on this interval between these two lines, I want to find the area in between here, or it'll be defined by the intersection of these in general. So that would be called the area bounded between f and g. So this is the area bounded between f and g. So if I ask you a problem, oh, find the area bounded between these two functions. What I'm talking about is you can sketch the functions, find out where they intersect, and in between that, find the area that is enclosed by both functions. So we want to talk about that. And you might recall way back when we were doing, I believe it was this lecture, was it this lecture? Yeah, way back when we were doing integrals and we were figuring this guy out. We had this situation where we wanted to find the area of this thing, right? But it was too hard to get math to work out. So what we did was we actually found half the answer, technically speaking. We found half the answer to the area problem. What we want to do now is to complete this idea. So yeah, now I know how to find the area under the curve. I'm interested in the area of this blob, which means it has a bottom part. So what I can do is just define the bottom part to be some other curve. And so finding the area of this blob is really finding the area between two curves, right? I can think of these two functions as being separate. Okay, so there's a top portion and there's a bottom portion. And the integral told us the way to find the area below the top portion. Let's now talk about finding the area of the whole thing. So conceptually speaking, you can think of finding the area between curves as that kind of thing, really completing the solution to the area problem. And the idea here is the following. Well, let's say I have these two functions. So this is f and g. Now, I care about finding this area here. However, I can look at that as the following, okay? So I can look at that, let's move this actually over here. I can look at that as this way. That area will be if I take the area under F and then I subtract this chat box is in the way now. And then I subtract the area under G, right? So I pretty much take this green part, subtract that part, and I'm left over with that part. Now for each of those, I actually know how to actually compute those. So I do know how to find the area under F. That's just the integral from A to B of f of x minus now I know how to find the area under G. That's just the integral from A to B of g of x dx. And now what we remember, hopefully, is that integrals distribute across sums. So this is really another way of writing this. And so that's our guy. And so essentially, suppose f of x is greater than or equal to g of x on AB, right? So let's say f is the top function. G is the bottom function. Then the area between f and g on AB is given by this integral, the integral from A to B of f of x minus g of x. Now, I don't want you to get totally hung up on the names here, but it's nicer if you remember it's something like top function minus bottom function. That's how you want to think of it. So don't worry if I call something f, but it's actually on the bottom. I don't want you to take f minus g. It's always the top minus the bottom. right? You always find the area under the larger one, subtract the area under the smaller one, and you would be left over with the area in between. So that is how we would go about doing area between curves. So let's actually do an example. So find the area between these two functions, y equals x squared and y equals radical x. So you could have a problem that looks like that, okay? Now you're going to want to determine who's the top function and bottom function, because that is the main idea. I would think of this as the main idea. And so you are interested in knowing who's the top function and bottom function. One of the quickest ways to actually do that is to just actually sketch the functions. We know what y equals x squared looks like. So that's your y equals x squared. And we know what y equals square root of x looks like. Right. Throw back to quiz 1. So essentially, the area bounded between the two curves is going to be this area here. So this problem is actually asking you to find what is the area of that portion right there. So from here, you can identify that your y equals the square root of x is your top function. And y equals the x squared is your bottom function. Now, what you need to do afterwards is find intercepts. Right? So we actually want to know what these coordinates here are, so I can figure them out here. How would you go about finding the intercepts?
Would it be when the two functions equal each other?
Yeah. Yep. Set them equal. Do you guys know how to solve that? What's the solution here?
Well, if you, it's hard to find the exact solutions, except I can think of 2 points that could be in general, because if you
Which
try
is?
to take the, it would be 0 and 1.
0 and 1 would work. So this one you can tell by expression that 0 and 1 would work, and it's pretty much the only points that will work. Notice that these two will never actually meet again. So you see 0 and 1, that's actually the answer. How would you get to that from something like this? Well, the normal strategy is get rid of the radical. You could square both sides. Then move that one to the other side. Then do that. Then from that, you get x equals 0, or you get x cubed equals 1. So this means that your x equals 1. So those are the intercepts. And we are going to take those guys and plug them in. So here it's 0 and 1. And so now we can actually find the area between these curves. So the area is going to be equal to the integral from 0 to 1 of top minus bottom. This is going to be 0 to 1 of the top we know was the radical of x, minus the bottom was the x squared. Okay, how do we do that integral?
We can actually separate it into 2 different integrals. One would be the integral from 0 to 1 of square root x dx, and minus, and then the next one would be the negative integral from
Yeah.
0 to 1 of x
Yes, that's
squared
true.
dx.
You don't necessarily have to write that out though, but yes, essentially what you're going to want to do is you want to think of doing them one at a time. Although if you don't write this line, but you just know in your mind you're doing these one at a time, it's also okay. But yes, that's what we do. Worry about them one at a time. So let's worry about the square root of x. What is that integral? How do you find that?
So it would be x to the power of 1/2, and then you just add 1. So it would be x to the power of 3/2, and then divide by 3/2.
Right, which is the same as multiplying by 2/3.
Yeah.
X squared, again, that's nothing to do here. Add 1 to the power, divide by the new power, and then you do that. And so now what you're going to do is you're going to plug in the 1. And subtract when you plug in 0, but plugging in 0 everywhere is going to give you 0. So you are going to get 1/3 as the answer. 2/3 minus 1/3. 1/3 is the area that's bounded between those curves. Yeah, so that's another application of integrals. You can find the area bounded between two curves, and there are all sorts of situations in which that would be something that you'd want to do. Even in applied math circles. So this might seem like something that's very mathematical, but some like probability and statistics, being able to find the areas under curves is very important, as it would turn out. I don't know if any of you have done classes like that, and though that's applied math, but they use that in the real world all the time. But this isn't a statistics class, so I won't talk about that. But yeah, being able to find areas under functions, very important. And it goes back to the roots of what the integral was talking about. So it's an example, it's an application that we want to talk about. General principle is essentially this: integrate the top function minus bottom function. There are other variations on this where you have to tilt your head to the side, but we're not going to do that in this class. That is basically it. You want to find the area between two things. Find the endpoints on which you can identify a top function and a bottom function, and then you're going to integrate from the top function minus the bottom function, and that's it. So this shaded area here is actually 1/3 square units large. Here's another application: finding the average value of some function. Now, I'm talking here specifically about the mean average. Again, something that you'd see in statistics and probability. So we know about the mean, right? I give you a bunch of numbers, then you add them up and divide by the number of numbers there are. This is known as the mean average. And if we have like a finite number of numbers, like n things, like if I give you 10 numbers, you can do this. What if you had an infinite number of numbers though? And that's what we're going to look at here. And again, you might wonder, well, why would I need to average an infinite number of numbers? Well, again, applied math, probably in statistics and many other spheres, actually need you to be able to do this. So a lot of times you are tracking something and the answer comes to you as a function, so you have to actually find the area under this function or the average value of this function, because you want to talk about in a statistical analysis, oh, on average, this is what's going on, right? So these are the outputs that we've tracked over the past 10 years. On average, this is the value that we see, right? So things of that sort. So if you have a lot of data points, and I do mean a lot, like it could be that you created some continuous function to model some situation, and you actually want to find the average of that continuous function. How would you actually go about doing that? Well, you want to find the average output. That's what we are going to look for here, the average output. So imagine that we have a function. So here's our function, and we can pick some x values, right? So we can pick like x1, and this is going to be f of x1. And So this is our function f of x. And then there's another value over here, x2, and we can pick f of x2, right? And then there's an x3, and then there's f of x3, and so on and so forth. And the question is, what is the average of these numbers over here? Okay, so there are a bunch of y values being outputted here, and there are a lot of them. For each x here, there is going to be a corresponding y, right? There will be a lot of them, more than you would want to have to add up by hand and divide by the number of numbers there. Okay, so the question is, what is the average of the y value that we're seeing here? So, in other words, i.e., we want to compute well, if I were to take f of x1 plus f of x2 plus ... plus f of xn and divide that by n, what would that be? And especially if my n is going off to infinity. What if there are a lot of these numbers? There's really a lot of them. How can we actually talk about what this value would be? Well, here's something. Recall, when we were setting up integrals, we had a quantity called delta x. This measured the length of a subinterval. This was actually b minus a over n. And so from this, I can solve for n. And this would be b minus a over delta x. And so what I can do is I can take this expression, I can plug it in here. And what would happen? So let's call this, I don't know, f average on AB. So we want to compute that guy. Okay, so now plugging that in, I would have this f of x1 plus ... all the way down to f of xn. And then in the bottom, I would have b minus a over delta x. This is going to be my average f. I can flip and multiply. So this is f of x1 plus ... f of xn times delta x all over b minus a. Now there's another notation we can write for the top. That is just taking a summation of all of these f's. I goes from 1 up to n times delta x. And at this point, you're like, gasp. Right? Let out an audible gasp. That's a Riemann sum. And in fact, if we let n approach infinity of a finite Riemann sum, we know what that gives us. That actually gives us the integral. So this is actually the integral from a to b of the function divided by b minus a, which is the length of the interval. So this means we have the average value of a function. So we have a real function where there's a lot of outputs, a continuous number of outputs. For every x you can think of between a and b, there's an output. This is equal to 1 over b minus a of the integral f of x dx. And so that is the takeaway. So I can find the mean average of a function, which you can just think of as just something that's outputting a lot of numbers. And I can still average that, and I can use the integral. the integral, after all, if you think about how it came to be, it's really just a way of adding things up very efficiently. It's really just an efficient way of adding up a bunch of things. So an average involves you adding up a bunch of things and then dividing by the number of things there are. In this case, the number of things there are is the length of the interval that you are adding stuff up over. And so that's the average value of a function. So for example, find the average value of y equals x squared on, say, 0, 1. Okay, so you have y equals x squared between 0 and 1. So you're focusing on this part of the curve here. Now, for each x value between 0 and 1, you are getting some outputs happening, right? So you're hitting a bunch of y values here, and we want the average of these outputs. Right? So when x equals 1/2, the output is 1/4. And when x equals 1/10, the output is 1/100. So you're adding 1/4 plus 1/100 plus 1/x squared, not 1/x squared, yes, plus 1/x squared because we're in 0 to 1 for all x's. So we want to just add up all of these y values here and then divide them by the number of y values there are, quote unquote. What is the average output, right? So if you were pulling a slot machine and it's just going to plug in a random number between 0 and 1 into y equals x squared and plop out a number on the screen, and you were to gamble and bet what number would pop out, this is probably the number that you should bet. Or at least if you wanted to bet a range of numbers, is there a small window where you'd expect the result to occur? You're going to center it around this value, right? So your mean average is a measure of central tendency. Again, getting too much into statistics. Let's actually just stick to the calculus. We want to find the average output of y equals x squared on this interval. What we would do is we would use this formula. So we know here that our f average, this is just going to be 1/b minus a, integral from a to b of our function dx, where in this case, our a and b are 0 and 1, respectively. So this is 1/1 minus 0, integral from 0 to 1 of x squared. So that's just the integral from 0 to 1 of x squared. And that is going to be x cubed over 3 between 0 and 1, which is 1/3. Now, if you were to ask someone who doesn't know about calculus and probably doesn't know too much about functions here, what they would guess the average is, the typical person would probably guess 1/2, right? So between 0 and 1, the maximum output is actually 1, right? So when you're trying to measure the average here, you're just measuring the average of a bunch of values that are showing up between 0 and 1. And so if you ask someone, what do you expect on average the output should be? Most people will, 0 to 1, it'll probably be somewhere in the middle, be like 1/2. Nope, it would be 1/3 actually, right? So, and that's because of how this curve is curving. So you see the farther along you go, the slope gets higher. And so it's not equally weighted along this curve. If it was just a straight line connecting these 2 points, the average would be 1/2. And you could actually do the integral to see that. But if you have the behavior of a function changing its behavior in this thing, and you want to know on average, what is it doing? The integration is going to give you a much better answer. It's actually 1/3. So the average output here is going to be 1/3. And yeah, that's it. So these are the last two applications, and this is the last thing in this course. Yay, we got to the end. We actually did a little bit more than I did last time, because I don't even think I spoke about this the last time I taught the class, but I'm glad we got through it. So yeah, area between curves, main idea, integrate top function minus bottom function. And for the average value of a function on some interval, it's 1 divided by the length of the interval, and just integrate the function on the interval, and that will give you the mean value. Other than that, this is something that we looked at last time, using integrals to solve like position, velocity, acceleration problems. But yeah, that is it. We are kind of, yeah. So we're done. That's the end. This stuff is not on your test. I'll probably throw it on the bonus, but there'll be questions on this on the final. But I'll probably put this section, except for this. I think this is on your test, which we covered last time. Questions like this, anyway. So up to this question is what you need to know for your test, which we covered last class. This is some extra stuff. For the next test, you can ignore it, although I might throw some bonus problems on this sort of thing. And yeah, we are done. So yeah, we got through it. That was Calc 1, ladies and gentlemen. We covered a decent amount of topics. These are the topics typically covered in 1203. We got through everything. Now you know everything. All right. Okay, that being said, so I was talking for a long time here. Any questions on any of this? Comments, concerns, questions?
I have a question about differential equations that we did like in March.
Okay.
Like a while ago for exponential growth and decay.
Yeah.
We did like so I'm talking about the equation, the derivative of p equals negative rp.
Yes.
So,
and that's all it is. P prime equals RP. This is for growth. And for decay, it's P prime equals minus RP. Now, what this means and what to actually do with it, you don't need to know. You just need to actually know this equation and know how to plug things into it.
So would a question like explicitly say like, what is the differential equation?
Yes.
Okay.
So it will say something like, it will describe a situation to you. So it might say, a radioactive substance has a half-life of 3,200 years. And if you start with 100 grams of the substance, then it'll go into some parts. Usually for a question like this, I'll ask you some parts. So one part will be find P of t, the amount remaining after time t, amount remaining after t years. B, describe the quantity with a differential equation and initial condition. And then I might ask you something like, how much is remaining after, how much will remain after 27 years, let's say. And then probably how long before we have, so start with 100 grams, 1 gram remaining. So that's a very typical type of problem that you'll see here. So in terms of differential equation, it's just going to ask you to state it. So we pretty much know that for A, we would use half-life equals, I think we use a different notation. We use T sub H. So for A, we would say, okay, the half-life is ln2 over R. This means that 3200 is ln2 over R. This means that your R is ln2 over 3200. So that immediately gives you the P. So you know that P of T is equal to P naught e to the minus RT. We know it's minus RT because it's decay. We know it's decay because it's a radioactive substance. We started out with 100 grams. And so that is how much remaining after time T. Now in B, if you want to set up the differential equation, you would just write P prime equals, you plug in the R, minus ln2 over 3200 P. That's your differential equation. Initial condition is at time equals 0, we had 100. That is your answer for part B. And then how much will remain after 27 years? So in part C, you just want to find P of 27. And that's your answer. And in part D, how long before you have 1 gram remaining? So you set 1 equals 100 e to the minus ln2 over 3200 t. And then this means that 0.01 is equal to e to the minus ln2 over 3200 t. This means that ln of 0.01 equals minus ln2 over 3200 t. This means your t is equal to 3200 ln 0.01 divided by ln2 years. And that's the entire problem. And this, by the way, is very representative of the level of difficulty a problem like this would be. So you should be able to get through something like that relatively as quickly as that. But for the differential equations part, you don't really need to know about differential equations. You just need to know the statement of the equation and know that you can plug stuff into it. Also know that it is the growth rate of the function. So if someone asks you, what is the growth rate when there's 50 grams left, then you'll take this equation and you'll plug in 50 here for P.
Professor, do you mind just scrolling down? Thank you.
Yeah.
What about the doubling time equation? Like, we didn't really go over that in class that much. Do we need to know that, or?
Yes. So doubling time actually has a similar equation to half-life. So the doubling time is ln2 over R. So if you know the doubling time, you can find R. It'll be how you would use the doubling time in a problem would be very similar to how I use the half-life in this problem. The only difference is, in a problem where there's doubling time, that means it's growing, which means you would not have a negative power here. You would have the positive power. But if I had instead, this thing doubles every 3,200 years, and we start with 100 grams now, and I kind of left everything else exactly the same, the solution would look exactly like what we have here, except you won't have a negative sign. And your solution here would look a little bit different because you won't have 0.01 in here, I think, because I would get something bigger than 1. But essentially, you'll have the same thing. So doubling time, the equation that governs that is very similar to the equation that governs half-life. It's ln2 over R. The difference is, make sure your R is negative for decay, which would apply to half-life, and make sure your R is positive for growth, which would apply to a problem that asks about doubling time. Other questions? Okay, so I guess we'll wrap up there. As always, I will post the video and a PDF of these notes. So in case you missed anything, you can catch it. You guys know the plan for the test. Expect an email this weekend giving you details on how to actually sign up for it and just getting used to it moving around. And I will also let you guys know if I can get an extra practice test to you early next week, so you can just practice going through not only the problems, but also practice using the platform. And that platform will be the same protocol used for the final, and the final exam date has not changed. So whatever is currently in your syllabus, that's the date that it's going to be. Hopefully that answers all the questions for now. And as I just mentioned, we're not going to do anymore. So we're completely done. So Tuesday's class is going to be more of a Q&A session. And as far as Tuesday's class is concerned, you can even start going back and start studying for the final. Ask me any questions about the final or what it's, and that good stuff. So Tuesday's class is going to be sort of a Q&A. We don't really have any new topics to go through. But yeah, we are done. That is it. So I don't know if there are any parting questions. All right. If not, we will stop there. Thank you guys for dropping by on such an evening. It's still, I would go back to bed, but I have another class and a bunch of meetings after this, so I'll stick around. You guys have a good day. Do the practice test and be on the lookout for those emails this weekend. And stay safe. And I guess bye. Bye.
Thanks.
Bye, thank you.
All right. Take care.
Thank you, Professor.
Take care. I'll see you guys